Assalamualaikum dear students, and hello everyone, welcome back to the Learn Daily Physics. So previously we've talked about the quantized radii, so now we are going to talk about the quantization of energy. So the quantization of energy, today it will be interesting topic today. So since the total energy is equal to the sum of kinetic energy plus potential energy, and let's see that as the kinetic energy E of n, we said, is equals to kinetic energy plus potential energy. Now this E of n is a constant term. For every n, for E naught, it is equals to 13.6 electron volt. We will see that how. So for every E of n, this term is a constant term. So when this potential energy increases, then what happens that this kinetic energy should decrease. How this kinetic energy decreases, that we have seen this kinetic energy is half mvn square, and it is equals to, it also equals to the half of kze square over rn. But this v of n square is, we can say that, is a dominant term. Velocity term in the kinetic energy is the dominant one, whereas in the potential energy, when we are talking about the potential energy will be equal to this minus kze square over rn. So let's say that kze square over rn. So I told you earlier that in the previous lecture, when we discussed the radius, that we seen that R of H is greater than R of helium and R of lithium, whereas the R of velocity of lithium is greater than the velocity of helium and greater than the velocity of hydrogen. It means that the radius, the greater will be the radius, the smaller will be the velocity. As the hydrogen have the greatest, you can say, radius, its velocity is the smallest one. Okay, so now when the velocity, this is the reason that when we have a negative sign with this potential energy, which means that when this R of n increases, when this R of n increases, this means that this potential also increases. Okay, so when this potential increases, this means that there is a negative sign here. This means that R of n will make, when R of n increases, then potential energy increases. As the potential energy increases, what happens to the kinetic energy? The kinetic energy will decrease, because the overall term here is constant. For example, we have a 20 here, and 20 is equals to 10 plus 15. Okay, so as this will become, this increases, this term increases, this 15 increased to 17, then or 10 plus 5 plus 15, 5 plus 15. So as this term 15 term increases and this goes to 17, what happens to this term? This term decreases and the overall terms remain constant. So as Rn increases, this potential energy increases, and because of that increase, the kinetic energy decreases. So as we've discussed earlier, or I've described you earlier, that as the radius increases, the velocity term R of n increases, the V of n decreases. So this is the main reason and the main thing that Bohr gave us, that as the radius, for the smaller radius, we have a larger velocity. So let's talk about the quantization of energy, and let's see that how energy is related with the n and z. So in the every equation, at the end we have to find out the relation with the n and z, as here we have done with z of n, and here previously we've also find a relation between n and z. Here you can say we have find out the relation for the radius, and now we are going to find out a relation for energy. So now in the kinetic energy, we said that the kinetic energy is equals to half of kz e square over r, and from equation number 1 in the previous lecture you can see that this is equation number 1, and how I told you that I'm going to use that in the quantization of energy. You have to keep that in mind. So how this equation is formed, you have to go for my previous lecture in the Bohr's atomic model, and you can see this there. So putting this equation from equation number A in the previous lecture I have described. So now for the potential energy, what is the potential energy? We know that the potential energy, for the potential energy, we say that the potential energy is equals to the work done by the unit charge for bringing it from infinity to that point. Just like this is electric potential energy, just like elastic potential energy. What is an elastic potential energy? When you stretch something, it store that energy from your body, and the work done from your hand is stored in that elastic. So that is the elastic potential energy. Same like that, when you take an electron from some point to other point, you have done some work on it, and that work will be stored in the form of electric potential energy. So this is the potential energy. So we know that the work is equals to force into displacement, and this is the force F, and this is the displacement. The force will be the Coulomb potential, and the displacement will be R of n. Now let's talk about what is the angle, what will be the angle between this. So we see that the force from this positive charge to this electron here revolving in the radius like this, the force will be in this direction and its radius will be along r like this. Okay, so if we are talking about the Coulomb potential, we can say that the force, attractive force, and it will be force will be the from positive to the negative, and the radius we will along like this, and they will have a negative sign. Theta will be 180 degree here, and it will have a negative sign here, and potential energy will be equals to minus k of z. This Rn will be cancelled out with this one, and minus k of z ze square Rn. Now the main confusion which will come in your mind, that where this half of kze square Rn comes from. Okay, this is the value of potential energy we have put here. Here we have find out this value we have placed here. But where this equation comes from equation number A. From equation number A, in the previous we have talked about this equation. So this is that equation. I told you that this equation is very important, we are going to use in next lecture. So putting this value of kinetic energy, and it will comes out to be, when we'll subtract, it will be a negative half of kze square over Rn. So now what we are going to do, we are going to put the value of this R of n we find out in our previous lecture, which was equals to this term here, equation number 4 we have talked about. Okay, so putting out this value here, so our final equation will be this z into z will be z square, and e square into e square e4. So mk square z square e4 over n square h cut square. So what we have to do, we have to separate constant on this side here in the bracket, and the variables, we can say that the changing terms, which is z and n. So for every atom, z is different and n is different, n could be different, but this m is same. M is a mass of electron, k is you can say that the constant for the Coulomb potential. So E, this is E4, it is also a constant term. So these terms are the constant one while these ones are changing. So we take the constant term here and the variable one here. So this constant term, when you put the values of these constants, so it will equal to it will be equal to 13.6 electron volt. So as this is this is energy and electron, it will be in the electron volt. So this is the whole square, and you can say that for the hydrogen this Z is equals to 1 and N is also equals to 1. So the energy for the hydrogen is given by putting this 1 1, and it will be minus 13.6 electron volt. So this is the ground state energy for hydrogen. So and we have find out the ground state energy for the hydrogen. So Bohr successfully told us about the radius and the quantization of the radius and the quantization of energy, but the Bohr